Let's start solving the problems. We are starting with 1122 of our book. It says a shell and tube heat exchanger. So it is a shell and tube heat exchanger. Must be designed to heat 2.5 kilograms per second of water. So one fluid is water and the water will be heated up. It means that water is the cold fluid because we need to heat it up. So water is the cold fluid and it will be heated up from 15 degrees Celsius to 85 degrees Celsius. So therefore T cold in would be 15 and T cold out would be 85 degrees Celsius. The heating is to be accomplished by passing hot engine oil. So the water would be the cold fluid and this engine oil would be the hot fluid, which is available at 160 degrees Celsius through the shell side of the heat exchanger. It means that water will flow through the tubes and the hot engine oil will be the shell side fluid and it will be available at 160 degrees Celsius. It means that it will come in at 160 degrees Celsius. So I will show you the solution at the same time. So we have the tube side fluid, which is the water, or we may also call it cold fluid, and then the next is the fluid on the shell side, which is the engine oil, and the cold fluid comes in at 15 degrees Celsius and the cold fluid goes out, it leaves at 85 degrees Celsius, whereas the hot fluid engine oil comes in at 160 degrees Celsius. The oil is known to provide an average convection coefficient of H0 is equal to 400 watts per meter square Kelvin on the outside of the tubes. So between the outer surface of the tubes and the oil, the convection coefficient is 400 watts per meter square Kelvin. 10 tubes pass the water through the shell. So there are 10 tubes in all. Each tube is thin walled. So as soon as we see the word thin walled, that will probably be a reference to the fact that the resistance of the wall would be or may be neglected if enough data has not been provided, as we were doing in previous chapter, which was on thermal networks, chapter number 3. So each tube is thin walled. So the inlet temperature of the cold fluid would be 15 degrees Celsius and outlet temperature of the cold fluid would be 85, and the inlet temperature of the engine oil is given us as 160 degrees Celsius. Now it says 10 tubes pass the water through the shell and each tube is thin walled, and as I have just told you that it is probably an indication that the thermal resistance, conductive thermal resistance due to the pipe wall or tube wall would be neglected if the parameters are not provided. Of diameter D is equal to 25 millimeters and it makes 8 passes. So each tube is making 8 passes. There are 8 passes. So as soon as we see that there are 8 passes, so therefore the correction factor would come into play and we would be calculating the correction factor for log mean temperature difference. It makes 8 passes through the shell. Now if the oil leaves the exchanger at 100 degrees Celsius, so oil was coming in at 160 degrees Celsius and after leaving and after giving away the energy to the cold fluid, which is water, it is leaving at 100 degrees Celsius. So it means that 100 degrees Celsius would be the value of TH out. That would be the value of TH out. So TH out would be 100 degrees Celsius. So they are asking what is its flow rate, means what is the flow rate of the hot engine oil. So we need to find out the mass flow rate of the hot fluid, means MH, M dot H. How long must the tubes be to accomplish the desired heating? So we need to find out the length of the tubes through which the water is flowing. So So that is all the data that we have discussed. Mass flow rate of the cold fluid means water is given to us as 2.5 kilograms per second and it is making 8 passes. There are 8 tube passes. So we need to find out the length of the tube. So moving forward, we will first calculate the average temperature so that we can find out the properties. And over here we will first be finding out the heat rate. So heat rate will either be found out using the parameters of the cold fluid or the parameters of hot fluid, and it will be found out using simple expression of mc delta t. So it may either be applied on the cold fluid or it may either be applied on the hot fluid. So since we are given the mass flow rate of the cold fluid and both the temperatures of the cold fluid, although we are given both the temperatures of hot fluid as well, but we do not know its mass flow rate. So therefore we will prefer applying Q is equal to mc delta T over the cold side fluid means water, so as to find out Q. And once we find out Q using this method, we will put the same Q for the hot fluid means engine oil, and then we will be able to find out its mass flow rate means the mass flow rate of the hot engine oil. So therefore, in order to find out the only property which is the specific heat capacity of the cold fluid, which is water, we need to find out the average temperature of water. Now the one temperature at which it is coming in is 15 degrees Celsius and the other temperature at which it is going out is 85 degrees Celsius. Therefore average temperature would be 15 plus 85 by 2 means 100 by 2 means 50 degrees Celsius. 50 degrees Celsius translates to 323 Kelvin. So now we need to go to the property table. Now we need to go to the property table of water. So we will go to table A at the end of our book, and at 323 Kelvin, if you can see over here, we have got temperature of 320 and then the temperature of 325. At 320, specific heat capacity of specific heat of water is 4.18, and at 325 it is 4.182. So at 323 it would be 4.181, or you may very exactly interpolate it. So it would be 4.181 kilojoules per kg per Kelvin. So if we put and I have calculated other property as well, because we might need it in the later in the calculation of Nusselt number, just like we used to do it in the chapters of convection heat transfer. So if we put that Cp as 4.181 exponent 3, you need to work the units out. So the mass flow rate is in kilograms per second, and if we put Cp specific heat in joules per kg per Kelvin, and this temperature difference may be put either in Kelvin or degrees Celsius, because that 273 will eventually get cancelled out. So we will get watts, we will get the units of watts. So Q will then be 731,675 watts. Now we will equate the same Q to the hot side fluid. So we will write it in terms of hot side fluid. So then we will write it as Th in minus Th out, whereas over there we were writing it as T cold out minus T cold in. The reason is that T cold out would be greater than T cold inlet temperature, and over here the hot temperature, the inlet temperature of the hot fluid means Thi would be greater than the outlet temperature of the hot fluid means Th outside. So if we put the same thing over here, we will get the mass flow rate of the hot fluid as 5.1 kilograms per second, but we need to find out the Cp of the hot engine oil first. Now Cp of the hot engine oil will be evaluated, will be seen from the same table of properties, but at at average temperature. So the average temperature of the hot engine oil would be the average of 160 and 100. So 160 plus 100 by 2 would be 260 by 2 means 130 degrees Celsius, which would be 403 Kelvin. So now we need to go to that property table and we will go to the engine oil, and it is there in table A5, and the temperature was 403 Kelvin. So at 400 Kelvin, the value of Cp is 2.337, whereas at 410 it is 2.381. So we will perform interpolation for a temperature difference of 3 Kelvin from 400 Kelvin. So it will come out to be 2.3502 kilojoules per kg per Kelvin, and we will put this value of 2.3502 over here so as to get the mass flow rate of the hot fluid. Now, so we have found out the mass flow rate of the hot fluid, which was one of the unknowns. The second point is to find out the length of the tube through which the cold fluid means water is flowing. Now the length means finding out the area, right? And area would be found out using Q is equal to UA delta T. So we need to in fact make a sequence of what we need to find out towards the last, and what intermediately we would be finding out in order to get the final answer. So over here the task is to find out the length of the tube through which the cold fluid water is flowing, and in order to find out this we need to find out the area. Now area would be found out using Q is equal to UA delta T, but UA delta T would be written as UA times LMTD, because over here, as discussed in the theoretical section, delta T will not be a simple delta T because there are 4 temperatures involved. So therefore the representative delta T is in fact log mean temperature difference, and on top of that, since it is having multiple passes, so therefore we need a correction factor. So LMTD for counterflow would be calculated, and that LMTD for counterflow, over here CF means counterflow, and that LMTD for counterflow will be multiplied with the correction factor, and this will give us the log mean temperature difference, equivalent temperature difference for this shell and tube heat exchanger with 8 passes. Area of course would be pi dl. Area would be pi dl because it would not be pi by 4 d square, because convection heat transfer will be taking place from the surface area of the tube, which would be pi d times the length of the tube, and n would represent the number of the tubes because there are 10 such tubes. Now we need to find out log mean temperature difference. So this is the point where we will find out area, and in fact area has got length. So if we find out this length, we will be done with the problem. Right? So but there are 2 unknowns over here. We may take diameter as 25 millimeters, which was provided in the problem. So over here we have got 3 unknowns. We do not know the overall heat transfer coefficient, we do not know the log mean temperature difference, and we also do not know the correction factor. Once we find out, Q is known because Q has been calculated as 73165 watts. So once we find out 3 unknowns, we will be done with the problem. So let's find out log mean temperature difference first. So we will make the figure of a counterflow heat exchanger. Although for some of the tubes it would be counterflow, and some of the tubes it would be parallel flow, as I had explained in the theoretical part. And that is why, for this reason, we calculate, or we rather introduce correction factor, which will take care of both the flows. So T hot in, T hot out, so this would be the direction of flow of the hot fluid, and this would be the direction of flow of the cold fluid. Cold fluid will come in at 15, it will come out at 85 degrees Celsius. Hot fluid is coming in at 160 and it is going out at a temperature of 100 degrees Celsius. So we need to find out delta T at this section. We will not be calling it inlet section. We could had called it inlet section if it had been parallel flow heat exchanger, because in parallel flow heat exchanger both the fluids enter at the same point and they exit at the same point. But in counterflow, inlet of one is the outlet of other and vice versa. So therefore we will not be calling it as this section as inlet, rather we may call this section as 1 and we may call this section as 2. So therefore over here we will be calculating delta T1, means delta T at section 1, and similarly delta T at section number 2. So delta T at this section would be the difference of 160 and 85, which will be 75 degrees Celsius or Kelvin, that would be the same thing. And similarly delta T at section number 2 would be 100 minus 15, means 85 degrees Celsius. So now we will calculate LMTD, which would be delta T1 minus delta T2 over log of delta T1 over delta T2, or delta T2 minus delta T1 over log of delta T2 upon delta T1. So the numerator will be written in the same manner the numerator has been written. The denominator will be written in the same manner the numerator has been written, because if in the numerator we have written delta T1 first, so then it would, in the denominator it would be log of delta T1 over delta T2, whereas if we have written delta T2 first in the numerator, just like we have written it over here, we have written it in the form of delta T2 minus delta T1, so therefore it would be log of delta T2 upon delta T1. So we will get log mean temperature difference as 79.9 degrees Celsius. So it is the equivalent temperature difference over the entire length of the heat exchanger. So we have found out log mean temperature difference for counterflow heat exchanger, and then we need to multiply it for with the correction factor. Now in order to find out the correction factor, we need to refer to those diagrams that I had shown you in the lecture, and this book is Yunus Singhal, where I had taken those graphs from. So I have shown you 4 graphs, and those graphs are over here. It is chapter number 13 of that particular book. So we have got this case where we have got one shell pass and multiple number of tube passes, multiples of 2, because there is a single shell. Now we need to calculate P and R. So P would be T2 minus T1 over T1 minus T1, and what is small t1 and small t2 and capital T1 capital T2? Small t1 is the fluid which flows through the tubes, and what is the fluid which flows through the tubes? It is water. So the water inlet temperature would be small t1, right? So if we look over here, cold inlet, water inlet would be small t1, and similarly cold outlet or water outlet would be small t2, right? And then capital T is the temperature of the fluid which is on the shell side. So we have got hot engine oil on the shell side, so its inlet temperature would be T1. So therefore TH inlet would be T1 and TH outlet would be T2. You need to write them in this manner so that you can calculate P and R. Otherwise it may be difficult to you to keep track of small t1, small t2, capital T1, capital T2. So now we will calculate P and R. So P is T2 minus T1 over T1 minus T1. So P is, if I take both on one screen. So P is small t2. Small t2 is what? 85 minus small t1 means 15. So 85 minus 15 over capital T1. Capital T1, as you can see over here, is 160 degrees Celsius. So T1 minus small t1, which is again 15. So we get this value as 0.483. Right? And then and then we will calculate R as well. Now what is R? As mentioned over here, R is T1 minus T2, capital T1 minus capital T2. So it would be 160 minus 100. So you can see over here it is 160 minus 100. And then the denominator is T2 minus T1, small. So it is T2 minus T1, so it is 85 minus 15 degrees Celsius. So in the denominator we would have 85 minus 15, so we get 0.857. So 0.48 and 0.85. So 0.48 would be somewhere over here. If I zoom it in further, 0.48 would be somewhere over here just before 0.5, and the other was 0.85. So we will go, so those are the curves for R. So 0.8 is this curve, and this curve pertains to that of 1. So 0.85 would be let's say quarter distance between these two, would be at 25% distance between these two. Now at 0.48, if I take this as 0.48 and then move upwards and then reach over here and then come approximately 0.25 back, so I can see that it is around it is about halfway between 0.85 and 9. It is about halfway between 0.85 and 9. Right, so we may take it as we may then take it as about 0.9 or just less than 0.9 or just less than 0.9, right? So if we take it as 0.9, because it is subjective, someone may say that 0.48 is not here, rather it is a little bit here. So there may be a deviation of like 0.1 or 0.2, but it would not be a very large deviation. So if I take it as approximately 0.9, so we have calculated F as well. Now the last thing is to find out U. Right? Now U, if you recall, I had shown you in the lecture that U would be calculated using this expression. Means we need to take care of the two convective coefficients, two convective resistances and one conductive resistance. Right? So over here we have reached to the point where we can, I will show you again, it says each tube is thin walled. So we would be neglecting the resistance of the pipe material. So since we are neglecting the resistance of the pipe material, we will then write it as in this form, where this log of R naught over Ri divided by 2 pi KL will get cancelled out. So it would be 1 over Hi Ai plus 1 over H naught A naught. And I had told you in the while I was explaining this particular slide that if inner and outer diameters are approximately the same, then Ai and A naught will approximately be the same as well. So that A will get cancelled out throughout. So it would be 1 over UA is equal to 1 over HI AI plus 1 over H naught A naught, and that area would get cancelled out throughout the equation. So we will be left with 1 over U as approximately 1 over HI plus 1 over H naught. That is only applicable if the resistance, if the conductive resistance of the pipe material is negligible. Otherwise we will calculate R or U including this pipe material resistance. So therefore U will then be written in this form. Now we are given the value of H naught as 400 because it was given in the problem. I will show you again. It was mentioned in the problem that the oil is known to provide an average convection coefficient of H naught is equal to 400 on the outside of the tubes. So outside of the tubes it is 400. So we need to find out the value of Hi, means the value of the convection coefficient between the inner surface of the pipe and the water which is flowing over its inner surface. So now all we need to do is find out the value of Hi, and as soon as we find out Hi, we will be able to find out overall heat transfer coefficient, and we will put that overall heat transfer coefficient in equation number 1 along with LMTD and correction factor, and we would be able to calculate the length of the tubes. Now if you look over here, the problem has again been to find out H. Means the problem has again come to the point where we are trying to find out the convective heat transfer coefficient, and this is the same exercise that we had done in the convection chapters 6, 7 and 8, or 7 and 8 rather. Particularly when we talk about over here, we are talking about chapter number 8. Why? Because it is the flow through a pipe, and chapter number 8 was about internal flow. So the problem has again boiled down to finding out the value of the convection coefficient H. And if you recall, we used to find out the convection coefficient with the help of the Nusselt number, right? And Nusselt number would be found out, would be calculated with the help of one of the expressions. So the same methodology will now be applied over here. So we will first find out, in order to select the appropriate expression of Nusselt number, we need to know whether the flow is laminar or turbulent. So we will first find out a Reynolds number. Reynolds number can be written either in this form, velocity into diameter upon viscosity, or this can also be written in this form, 4 times mass flow rate over pi d mu. And I had shown you in chapter 8 that how can we get from this point to this point. I mean, we can come from this point to this point by putting the velocity as in this form, as mass flow rate, using the continuity equation, simply saying. So over here we need to use this equation so as to find out the velocity, if you want to use this particular expression, or if you want to skip it and use this expression, you can do this as well. Right, over here what we would be needing? We would be needing the mass flow rate, which has been given as 2.5 kilograms per second, but kindly note that this 2.5 kilograms per second flows through 10 tubes. So we need to divide this 2.5 by 10, right, because we are calculating the Reynolds number through one tube, which would be the same through all the tubes, over pi d mu, and mu would be the viscosity of water. So mu needs to be calculated at in the same way the Cp of water was calculated, means at 323 Kelvin. So if we go to this particular table of properties and go to the section of water, and then at 323 Kelvin, so at 320 the value of mu is given to us as 577, and at 325 it is 528. So we need to interpolate it. Upon interpolation we will get a value of 547.6, and if you note, those values have been provided by multiplying with a million. So the actual value would be obtained if we divide it by a million. So therefore you will see over here that it has been divided by a million, means into 10 to the power minus 6. So that value of viscosity will be put over here, 547.6 exponent minus 6, and we get Reynolds number as 23251. So it is 23,251. So if you recall, if the Reynolds number through a pipe was greater than 10,000, so we used to call that flow as turbulent. So since it is greater than 10,000, it is 23,000. So therefore the flow would be termed as turbulent. And for turbulent flow, the expression of Nusselt number would be selected, which was 0.023 Reynolds to the power 4 by 5 Prandtl to the power 0.4. There were two expressions, Prandtl to the power 0.3 and 0.4, depending upon whether it is getting heated up or getting cooled down. So it is getting heated up over here, right? So you need to refer to that lecture. So at the end we will be able to calculate the Nusselt number as 118.978, and then as usual we will equate this Nusselt number to HL over K, or rather HD over K, because it is the pipe and not a flat surface. So Nusselt number is 118.978. The value of H is HI, which is the unknown. Diameter of the pipe of the tube is 25 millimeters, and K. So this would be the value of thermal conductivity, which we can get from the property table, and this will be 643 exponent minus 3 means 0.643. 0.643. Because you can see over here I listed the values of the thermal conductivities in watt per meter Kelvin, and at 320 Kelvin the value of the thermal conductivity is 640, and at 325 Kelvin it is 645. So you need to interpolate, and after interpolation we get 643 as it was written over here. And furthermore, those values of thermal conductivities have been listed by multiplying after multiplication with 1000. So the actual value would be obtained if we divide the value by 1000. So therefore it is 643 exponent minus 3 by dividing it by 1000. So we get HI as 3060.114. Kindly note that this K is not the K of the material, rather this is the K of the fluid which is flowing over the inner surface, means K of water. So that is why we have referred to the property table of water in order to find out the thermal conductivity of the fluid. So we will then put this H of 3060 over here. So it would be 1 over 3060 plus 1 over 400, and we would be able to get the value of the overall heat transfer coefficient using equation number 2. So we get it as 353.7 watts per meter square Kelvin. The units of U would be the same as that of H. So we then put it over here, Q as this value 731675, which was calculated. U is 353.759, so this value is U, times pi dl. So pi dia was 25 millimeters times L remains the unknown, and there are n such tubes, so there are 10 such tubes, times log mean temperature difference. So log mean temperature difference was calculated as 79.9 degrees Celsius, and times correction factor, which was calculated as 0.9 or 0.89 if someone remains a little less than 0.9. So therefore the length would be calculated as 36, that is the total length of the tubes, and since the tube has got 8 passes, I can show you that it was mentioned over here that each tube makes 8 passes. So the total length is 36, and if we divide it by 8 passes, we get the shell length as 4.5 meters. Right? So the total length of the tube is 36.6 meters, whereas the shell length would be 4.5 meters.